So my name is Julio Tino. I'm the Dean of the McCormick School of Engineering. And I would like to welcome all of you to the Davis Symposium lecture. I'm going to let my colleague, Mike Mixis, do a proper introduction of the speaker. But I wanted to mention a couple of things regarding the lecture and regarding fluid mechanics at Northwestern. A few moments ago, a website launched that describes all fluid dynamics at Northwestern. And I think in the front page, or what you see in the website, they will sell something from cells to galaxies or something like that, typifying the work of at least two people here. On the cell side, there are several people, and on the galaxy side, astrophysics, there is a new faculty in ISAM. There is fluid mechanics everywhere in engineering. Clearly in ISAM, that was the house of Steve Davis, still is. In chemical engineering, biomedical, in civil and environmental, a lot. In material science, in fact, Steve collaborated a lot with Peter Borges on coarsening and things like that. Mechanical, but also physics. I'm forgetting parts in here. And even though I don't think it appears in the website, there are components in earth sciences that have to do with fluids. So fluids is everywhere. And we wanted to capture all of that, but to capture things, sometimes you have to have a focal point, and the focal point is the Davis lecture. So we are delighted that we have this. We launched last year, and the speakers in the sort of initial symposium were listed in there, but from now on we'll have a distinguished speaker every year, and the speaker this year is Professor Harry Swinney. So I think it's very important to kind of get a sense of all the activities in this space, in McCormick, physics, math, and so on. And we need to bring someone who encapsulates the spirit of all the activities. And even though I'm not going to do the introduction, there are very few people who encapsulate this as well as Harry Swinney. So welcome to all of you, and I'm going to pass the mic to Mike Mixis. Thank you.
So welcome to the Steve Davis lecture. The lecture is in... Is this working? Oh, yeah. The lecture is in honor of the remarkable achievements of our distinguished colleague, Steve Davis. Steve has been a member of ESAM for over 40 years, during which time he has made fundamental and lasting contributions to fluid mechanics and material science. The lecture series is to honor Steve's achievements and to highlight those in our field who have continued to impact the science at a high level. This series started in October of 2019 with the intention of an annual lecture. Then came COVID, and we postponed it 1 year. When we started planning this in the summer, this past summer, okay, it was the hope to reproduce the festivities of the 2019 lecture, but then came Delta. But not all is lost, and we have much to be thankful for. Today, the lecture will be presented in person by Professor Harry Swinney, a sign of returning to normal. But COVID still is impacting the event. As you can see, there are no treats or drinks or a reception, and you're required to wear a mask in the room and drink only through a straw. I don't want to comment on that. Okay. But we learned last year that Zoom had some pluses in widening the audience, hence today's lecture will be on Zoom, okay, and given by Harry, okay. Harry is Professor Emeritus and the Sid Richardson Foundation Regents Chair in Physics at the University of Texas at Austin. Harry has made lasting contributions to both experimental and theoretical nonlinear dynamics, including chaos, pattern formation, internal gravity waves, bacteria colonies, and many other areas. And today, you'll hear about granular flows. He is, in the opinion of many, the best of the best. He is the person that comes to my mind when thinking of impactful and experimental, fundamental experimental results in nonlinear dynamics. He has been recognized within the community with many well-deserved awards, including honorary degrees. To mention just a few, the Guggenheim Fellowship, the Boltzmann Medal, membership in the National Academy of Sciences, and the American Academy of Arts and Sciences. The list goes on and on. His feed is quite thick. It should also be noted that he is the founding director of the Center of Nonlinear Dynamics at the University of Texas, Austin. I give you Harry Swinney.
Thank you. It's a pleasure to be here. I'm sorry that Steve Davis was not able to make it, but he's been a longtime colleague. I met him in 1969 at Johns Hopkins University. I was a postdoc, and he was an assistant professor, just joining the university. We really began to interact in the late 70s when our interest in systems, fluid dynamics and instabilities and pattern formation coincided, and we have interacted through the years, and it's been great pleasure meeting him at many conferences and in person, various places. So today I'm going to talk about a very simple problem, a collection of balls, identical spheres that are perturbed in some way, and we're interested in the problem of nucleation and the formation of a lattice, and how does this happen? And let me begin, though, by acknowledging the people who did the work. Let's see. Yes. That works? Yes. So Charles Radin is a colleague in the same building I'm in. He's a mathematician, and he came to my office some years ago and said he was interested, and had been interested in a long time, in nucleation phenomena, and wondered about studying nucleation in a granular medium. Would it be possible to construct an experiment in which the system was perturbed in some way and the particles begin to form crystallites? So I had a postdoc at that time, and we designed an experiment. Matthias Schroeder was the postdoc, and Matthias knew of a graduate student in Germany who might be able to come, and Frank Rietz came as a visitor from Germany to work on the experiment. And we worked on the experiment and got it up to the level of operation and collection of data. And Matthias Schroeder received an offer of a position at the Max Planck Institute, one of the Max Planck Institutes in Göttingen. And he moved there, and Frank Rietz went with him. But we continued the joint experiment online and on the telephone. And the data I will show today was actually taken in Göttingen. So we completed the experiment and published a paper. And there were a lot of open questions that we wondered if they could be addressed with simulations. So I had a former postdoc, Mark Shattuck, I talked with him. He was working in collaboration with Corey O'Hearn at Yale University, and Corey O'Hearn and Mark had a postdoc named Wei Wei Zhen, and they conducted simulations, and we had weekly online meetings to discuss the simulations as they went along over a period of 2 years. So, of course, we had research support from foundations and from federal agencies. Now, the story begins of arrangement of balls in a container, spheres in a container. It was a problem that was considered by Kepler. If you have a big box on the surface of a ship and you want to put cannonballs in it, and you want as many cannonballs as possible to fit into this box, what would be the most efficient packing? And he calculated that the most efficient packing would have 74% of the volume filled by these balls, and the rest would be space. So this is a geometry problem. You stack them in some way, and you come up with this number. And that's Kepler's conjecture. Now, if you stack balls, oranges, in a supermarket, you put 3 together in a triangle and on a flat surface, and you add balls in a natural way in the center and then around the sides, and you build up this arrangement, which is a crystalline lattice, and the volume fraction is just that was calculated by Kepler. Now, there are actually 2 possible lattices here, because the third row can be arranged just in the same way as the first. So you have A, B layering, and then A again, B, A, B. But the third row could be shifted with respect to the first 2. So you would have 3 kinds of layers, A, B, C, A, B, C. And that's an FCC, face-centered cubic lattice, and this is a hexagonal close-packed lattice. Either way, you have the same volume fraction. Now, centuries pass. You get to Gauss, 2 centuries plus after Kepler, and he tackled the problem of Kepler's conjecture. And he was able to prove that the conjecture is true. The most efficient packing of these balls in a container was the one that Kepler described. If the spheres are in a regular lattice. However, it's possible to arrange a group of spheres so that the local volume fraction, say taking one sphere as a reference and then the spheres right around it, have a volume fraction above that 74%, even above 75%. That's an irregular arrangement, but you can't make a lattice out of that irregular arrangement. So it remained unknown whether some irregular arrangement might be found that would have a volume fraction greater, that would violate Kepler's conjecture. Eliminating all the possible arrangements, though, irregular arrangements, is difficult. So, David Hilbert in 1900 made a list of famous, important, unsolved problems in mathematics. And Kepler's conjecture was one of these. Actually, it was part of the problem 18. Now, and this is just what I've said twice already, that's the most efficient packing. In 1998, a math professor at Princeton University, Thomas Hales, decided he would take on as a major project the proof of Kepler's conjecture. And he worked and talked with many others, and there was an international conference about how to approach this proof, how to do the proof. And a team was formed with these people in it to prove the Kepler conjecture. And it was called the FlySpec project. You can look online for information about it. They published this proof in 2017. And the team included people who were experts in automatic theorem proving and machine learning and various areas of expertise, looking at all possible arrangements of the balls to see if there would be something more efficient than the arrangement, the HCP or the FCC lattices. And concluded in this paper published in 2017 that Kepler's theorem or conjecture was true. So if you take a box of particles and just pour particles into it, you have some random collection of particles. In general, of course, they don't have to be identical. Here you have a box of particles that is mounted, in this case, on a shaker table. You can buy from various companies tables which shake the particles. Now you can do this, and you've done it, I'm sure, with your box of cornflakes or cereal in the morning. The material has settled in shipping. You can tap the box, and the level of the cornflakes drops. Right? It's an experience everyone has had. So now if you shake this box of particles, you see the level has dropped. And there are hundreds of companies that make shakers to compact particles. And the one that I came upon on the internet, and this is in many industries, in the food industry, grain, sand, salt, asphalt, concrete. Some are specialized, but do some regular perturbations, maybe shaking or oscillating horizontally, or other methods of making small perturbations of the original random collection of particles. You can compact them and increase the volume fraction. And this is the instrument I found. If you really want to shake something up, you buy a dodecacone. It has 14,400 horsepower, and you can drive a 30 meter diameter pile underneath a skyscraper or under airport runway in the swamp, and just compacts. It'll compact 15 meters in less than an hour, whatever the subsurface might be. So shaking makes the volume fraction larger. Now, so contents may settle on shaking, increasing the volume fraction as the perturbations continue. The first systematic experiments were done on collections of ball bearings in 1960 by two persons. David Scott was in Toronto, and Bernal was at University of London, and they knew one another. It's pretty clear. Look at their papers in Nature were 2 pages apart, back-to-back page papers. So, and Scott says, what's their motivation? Well, they would like to understand how crystals form in liquids, particularly just a simple liquid, a monatomic liquid. How do the crystallites form, and how does it freeze? And Scott became interested in this through Bernal. So Scott's experiment is the one I'll talk about. Scott poured ball bearings into a cylindrical container, and he recognized that, like putting oranges on a surface and stacking them, it's easy for the lattice to form. Now, if you're perturbing the system, shaking it, and you have a flat wall, you'll form a crystal on the wall, and then that grows. So to inhibit the crystal growth at the wall, he made irregular dimples on the wall, spaced irregularly, also irregular in size. And he increased the size of the container so there were more and more balls, and looked at the volume fraction in the limit of many balls. In fact, 20,000 balls, 1/8 inch diameter ball bearings, and he found, now as you make the container taller, this is the volume fraction occupied, and this taller the volume, the more particles you have. This last point here is for a cylinder with 20,000 spheres in it. The volume fraction approached, he saw 0.617, 61%, 62%. So there have been many experiments since then and since 1960. And here's a list of fairly recent experiments. And these did not make dimples or did not make the walls of the container irregular. So they got crystallization on the walls. But they were studying this problem. I don't know why they didn't do that. But they perturbed the systems in different ways. Some had container balls and would flow fluid through in an oscillating way up through the container balls, and then slowly decrease the amplitude of the oscillations of the fluid flow, and we'll get some result. But this is our experiment now, and we took a box, as drawn schematically there, with 50,000 glass spheres. They're very precise spheres. Well, to 0.1%, they're uniform in diameter. That's $25,000 worth of spheres, because they're 50 cents each. So we perturb the system, not by shaking it, but slightly oscillating this wall, so it goes back and forth. This is a degree of 20 degrees here, so our angle is actually 20 times smaller. Very small amplitude of oscillation here. Some fraction of the diameter of one of the spheres at the largest. So if you look at the sides, we're worried about the crystallization on the walls, and we have particles glued to the walls in irregular positions. And of course, you have to maintain a pressure in the system as it becomes more compact so they fill the container. So we did, and here's actual schematic of the apparatus. 10 centimeters by 10 centimeters by 10 centimeters. And this bottom plate here is oscillating back and forth, as indicated by a small amount to shear the system. And we look in to see the locations of the spheres by shining a laser light sheet, as indicated here, through here, a thin sheet, and then take photographs with a camera here. That's how the experiment is done. And we had hoped to see in the interior, away from the walls, the emergence of a crystalline cluster, a crystallite. So we oscillated the system now, and I want you particularly to notice this is a log scale. So this is the first oscillation. This is as the particles were poured into the container, the volume fraction was less than 63%. And with increasing shearing of the container, the volume fraction increases more or less monotonically. And this is 10 to the 4th oscillations, 10 to the 5th. We went beyond 10 million. We had several runs. This is one run. And this went to 2 million shear cycles. And we would stop with walls vertical and take a photograph of the interior of the cell. And that took a while because we had to take many photographs. So this took many months to run. And you see this increase, and there's a plateau there, it seems in green. And then at some point, the volume fraction begins to increase rapidly. But that's the kind of experiment that's been done since 1960. Many experiments have looked at this increase in the volume fraction. But we wanted to see where every single particle was in the cell. So with these, I was going to make an aside remark that one thing about a granular system is that under shear, like when you step on sand, you know, the sand rises around your foot. The materials increase in size initially because they have to get around one another, the particles do. And Osborne Reynolds discusses that very nicely in a 1985 paper. He called it dilatancy, because it dilates, the particles dilate. And this is shown nicely in an experiment in France in year 2000. So there are only 10 cycles here, but you can, with shearing, oscillating shear, you see that you reach a peak. This is every time the sidewalls were vertical, you reach a maximum. This is, say, with the sidewall moving to the right, and this is moving to the left, to the right, and so forth. So you have this oscillation, but a general increase in the volume fraction of the particles. And this is with fairly large angle for the tilt of the plates. But that really illustrates this Reynolds dilatancy very nicely. Now, we can determine the volume fraction for each sphere. And we do that by looking at the sphere. Say you have, this is cross-section of a three-dimensional system, right? And you look at this cell that is formed by drawing a line between the center of two particles here, bisecting that line with a plane perpendicular to the line. That's like that. This was a construction introduced by Voronoi, Russian mathematician, in the 1860s, shortly before he died. So that's one Voronoi face, and you can do that for all the nearby particles. So you have many Voronoi faces making up then a cell, which is the Voronoi cell. And you can look at the sphere's volume here relative to the Voronoi volume and see what that volume fraction is for each sphere. So a Voronoi cell in a collection of particles like this can have up to 18 faces, but in the crystalline lattice, whether it's FCC or HCP, the number of faces is 12. And, well, I've said it. That's a repetition because I've said that many times now. Now to see the individual cell, or particles in the cell, we match the refractive index of the fluid to the borosilicate crown glass 7, BK7 glass. And that's done with a mixture of esters. And at a particular wavelength of light, the wavelength of our laser sheet, 589 nanometers, refractive index is given there. And that's, of course, at a particular temperature. So at that temperature, the glass refractive index, and the fluid refractive index is the same. So you don't see anything when you look in to the cell. But if you pour in a little fluorescent dye, then the dye will enable you to see the individual spheres. So with a sheet of light, you get a picture like this. This is a portion, and we can take many of these sheets with the laser sheet rastered along through the cell. And that's what's done. So this is the full cell, and we're interested in, you can see the arrangement of the cells. Spheres near the walls not the same as that in the interior. So we look at the spheres in the interior and obtain 1,000 images like this across the cell. And we determine then from those images the coordinate of each of the spheres, 20,000 spheres, to within 3% of the diameter of a single sphere. So pretty precise determination of the whole set of sphere positions. And then we test each sphere to see what the volume fraction of its Voronoi cell is. And it's 74% if we have a crystalline lattice, but we're down in a total cell volume fraction of 65% or so, 64%. So we identified as being a crystallite or a local volume fraction that has potentially crystalline order. If its local volume fraction is greater than 72%, we could change that to 73%, and the result doesn't change much, or 71, whatever. It's not the results are not sensitive to that choice. But what about the orientational order? How are the spheres oriented? Well, you calculate that for each sphere from this sum of spherical harmonics for the nearest neighbors, for all the nearest neighbors, all 12 nearest neighbors. And if you have FCC lattice, this orientational order parameter has a certain value. And if you have hexagonal close-packed lattice, it has that value. So we determine either FCC or HCP for each sphere. Now, here's a shot from a movie. Let's see, can that front light be turned off? And this is as the particles were poured into the cell. And you see here two spheres that satisfy our condition. So of the 20,000 spheres poured in randomly, these two are locally in a lattice, satisfy just one sphere in the center of 12 particles, nearest neighbor particles. Now, that's as poured in. If we go further along, some later cycle, now we have, after shearing, 20, so we're right here, the green line shows that we have this collection, 12 single spheres satisfy the condition of being in a face-centered cubit. None of those that are in a hexagonal close pack, but 12 spheres, just single spheres. So it's much more than just in the poured-in sample. Now, we continue shearing. Each scan of the cell, making these 1,000 laser light sheets, feeding them in the computer and doing a little processing, takes 8 minutes. So doing 2 million takes a while. But we didn't make the scan for every shear cycle. We skipped some, because time constraints. So here you see the first appearance of a hexagonal close-packed lattice for just single spheres, two single spheres. See, it says 2, and they're 18 face-centered cubic after 31,000 shear cycles.
Laser pointer?
No. If that's okay. And now, see the first crystallite, and you can see it's hexagonal close-packed here. And this is after 190,000 shear cycles. Now, we go to 390,000 shear cycles. There's several little ordered clusters. And something we hadn't anticipated is that nearby or adjacent particles can be either an FCC or HCP. So, but you have orientational ordering. That you have the layers still, and every sphere that is shown has locally either FCC or HCP. And it has, of course, the density required. So, now this is just some pictures of, this is talking about the layering, which I said before. So you can have mixed layering, which has the same volume fraction. You can have all AB, AB, or you can mix in some ABC, 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 and then AB, AB. But there's still a well-defined orientation of each cluster. All of them have the same volume fraction. Now, this is much later, and you see the clusters are growing in terms of number of particles in a cluster, and this is really taking off. This is it. Well, this is 2 million. Now, so let's now turn to the simulations. So that was the result from the experiment. There were a lot of things we didn't understand, and we hoped we'd get some understanding by doing simulations of particles in contact with purely repulsive force when they make contact. And we took actually the limit to very repulsive force, so it's essentially hard spheres. We took a hard sphere limit in the simulations. Now, we have dissipation, but we didn't put in frictional dissipation. It's very hard because the particles can roll with respect to one another, stick friction, or you can have sliding friction, and who knows what the frictional coefficient is for each of the sliding frictional coefficients, each of the sliding particles. So just, you have to have dissipation. You're putting energy into the system through the forcing, and that is dissipated through, you have a fluid, so you have Stokes drag, you have a drag force on the particles. And so your equation of motion for each grain is this one, this interaction between the grains, the viscous drag, and gravitational term. So in the simulations, there were different numbers of spheres, and up to 18,000, and the container size is there. That's in terms of the diameter, 22 particles across, and as I've overemphasized, I suppose, that it's important to inhibit nucleation at the walls. So the particles on the walls were fixed in random positions, and initially the particles were in the poured-in state. That's where the simulation began. And because the particles are very stiff, you have to have many simulation time steps per cycle. You spend a lot of time varying the number because it takes a long time to do the simulations with so many steps per cycle. So the result is each of the spheres now in the simulation or in the experiment has its local volume fraction. So in a collection of 20,000 spheres, either experiment or simulation, you have a distribution of local volume fractions. And that's what's plotted here in this next slide. This is the distribution of sizes from both experiment, and that's shown, and that's a collection, these green points here. These are points for over a range of cycles from 19,000 to 67. So the probability distribution function is not changing. It's invariant through this shear process. In the simulation, I just showed one image there at 10,000 cycles, but you can see the points fall on the same line. And this curve here is, of course, a Gaussian. Oh, this is a Gaussian probability distribution for the sizes of the local volume fractions in the Voronoi cells. And you see that go up to 72. Well, there are some up above. Now, if we go with more shear cycles in the experiment, we saw the appearance of volume fraction here at 74%. So these have the crystalline order, local crystalline order. This is the volume fraction that had been postulated to be the most efficient. And there are some local spheres which have a higher volume fraction, up to 75%, or a little higher than that. And again, we see that the distribution functions in the experiment and the simulation are the same. Now, the experiment and simulation is different. The simulation, of course, is a model for the real experiment. There are different types of dissipation, and they differ in a number of respects. It's a model, but it is a pretty good model, you can see. Okay, so that peak is showing the appearance of the ordered clusters. Now, in the simulations, you can put on a number of simulations with different amplitudes of the shear. The experiment was 0.01, and then we went to 10 times higher amplitude in the simulations, and you see very quickly that this is only 10 cycles, not a million cycles. 10 cycles, you have volume fraction shooting up. If you have lower amplitude of shearing, not as big an angle, then the increase is slower. And if you get to something we're going to try to do in the simulation, the same amplitude of shearing as in the experiment, but it just took too long. This simulation in the computer for amplitude 3 times that of the experiment took many months, that simulation. And we did the error bars here from multiple simulations. So maybe 10, 8 or 10 simulations. And that is the mean that's shown. Now, the black circles show where crystallites are first seen in the experiment or simulation as you do increased shearing. And they appear very quickly with the large amplitude shear. And it takes longer and longer before you see crystallites with the lower amplitude shearing. And with shear amplitude of 0.03, we never saw crystallization. I mean, presumably we would, because in the experiment, we know there was crystallization, and yeah, it's not observed. Okay. Now, if you look closely at the percent of the total number of spheres that are in crystallites and plot that as a function of the global volume fraction, you see that crystallization starts around 64.6%. And these simulations with 0.04 and 0.05 are close to what you see in the experiment. In the simulation with 0.03, there's no crystallites seen, as I mentioned. So, let's see. Yeah. So we can look with the larger amplitude of shearing in the simulation, and you see the crystallization onset occurs earlier and earlier. But with sufficiently small amplitude shearing, the crystallization is about the same, even with 0.06, but with 0.01, 0.02, even 0.05. So it looks as though there's a convergence with sufficiently small shearing amplitude to a onset that is 64.6%. And that's what we identify as the random close packed. There are numbers for random close packing. I looked, there are hundreds of papers in the last 50, 60 years on random close packing. But what is the packing which is random close packed? And the numbers cluster around 64, 65, 63%. But this particular experiment yields a well-defined number, 64.6%. This is plus or minus 1. Now, I mentioned the dependence on shear amplitude. As you increase the shear amplitude, then the volume fraction at onset begins to decrease. And we can go further than this, but you get the trend of the dependence on shear amplitude. So with large amplitude, you have the crystallization appearing quickly, and the crystallites grow very fast, and small crystallites quickly merge with the large ones to make larger crystallites. Now, I did not have the experimental data on that slide, but if I put here the experimental data, you can see that it's in accord with the simulations too, as far as the onset of the crystallization where it increases. There's the 64%, there it is, yeah, 64.6% plus or minus a bit of uncertainty. Now, I think this is, we felt an important observation in that the crystals have to be, crystallites or clusters have to be of a certain size to take off and really grow. And that is about 10 spheres in a crystallite. These with a smaller number of spheres, 1, 2, or 3, usually don't last. It's all statistical, but they will disappear. But once you get above 10 in a cluster, then the growth really takes off. Okay. And you can look at the size of the largest crystal here, largest crystalline cluster as a function of volume fraction. And you can see here where the 10 falls, and that's this point. And the next largest, you have a largest, next largest cluster. And now if you look at the percent of all the spheres that are in a crystallite, you can see this 64.6%. And then the growth is rapid until the crystallites fill the cell, fill the sample volume. Okay. So, well, this is okay, I'll skip. One point I was going to make is the gravity doesn't seem to play an important role. We did simulations and, the experiments had gravity, but the difference in density of the spheres and the fluid was small, so it was not, the buoyancy was not significant, not large. But in the simulations, we could turn off gravity and the results were essentially. So gravity doesn't seem to play a role, at least an important role. Okay, so I'm concluding now. Order is defined here when a crystallite or crystalline cluster has the local volume fraction close to the 74%. In Kepler's initial estimate, calculation, and the Q6 value, the orientational order parameter for either of these lattices, either of the two lattices. Now, I've already said enough about suppressing nucleation, and I'm just repeating here that a certain threshold of particles, crystallite size is needed for it to take off and rapidly grow. And that's 10 particles here. Emphasize that. And here, I just want to emphasize that this is a number relevant for small amplitude forcing, and it could be in various kinds of forcing, but here it was shear, but it could be vibrations. And you have to have enough particles so that you're looking in the interior away from a wall. And in the simulations, we found it took about 6,000 particles, which is interesting because there were so many simulations of granular media that were done when larger computers became available in the 60s, 70s, 80s, 90s. But they had typically, in the early ones, 100, and then 600, and then 1,000 became a large simulation. But 1,000, you take the cube root, your particles that are away from the effect of the walls is a small number. But you get to 6,000 or higher, the wall effects can be neglected. So you don't have to have friction, you don't have to have gravity, no energy conservation. Now, real motivation for this work was, as it was for the work of Bernal and others, is to understand freezing in fluids, understand how water freezes. It's not understood. You can take water at 0 degrees C and it won't freeze if it's pure. You can cool it, super cool it down to 48.3. But if you have a little nucleus, that nucleus will grow very fast. How many particles are needed in that nucleus for it to rapidly grow? Nobody knows. Okay. And there are various references on this point. Now we could see in the simulations and in the experiments, when you have two crystalline clusters and one large and one small, and they are close to one another, the smaller one loses atoms, loses spheres, to the larger one. So they go from the small to the large. The larger one, in a sense, gobbles up the smaller one. Does that happen in freezing? I don't know. So there's something called persistent states, which are not understood. And then there's a question of, is this random close packing defined theoretically? And the answer is no, it's not defined theoretically. But there are a lot of things which are not explained in experiments, which may someday be explained. It exists in our experiment and many experiments, hundreds of experiments in the last 60 years. There is a maximum random volume fraction, and it's an open question for the students. It's a homework problem. Okay, with that, I'll conclude. Thank you very much. I appreciate your attention.
Hi, I was curious, so you said in the experiment you're not, sorry.
Can you pull your mask down just a second?
In the experiment, you said you weren't tracking at every oscillation.
Every cycle.
You are tracking at every
Yeah, we're not.
We're not, okay, so.
We did it for a few cycles at times, but you don't learn anything.
Okay, well, I guess that's what I was gonna ask is
Yeah.
do you know about the history of each crystal, maybe from the simulation?
From the simulations, we know the history of each crystal, and there's a lot to be yet gleaned from the simulation data. Right.
Yeah, I was just curious. I guess you had at the end, you had a little bit about how frequently you lose particles versus how frequently they stay intact. Could you say just a little more about the dynamics or what you have so far?
We're looking from step to step in the simulations for growth, and we did look, and it was with 6 or 7 particles, you could go either way, but typically with less than 10, the cluster would disappear. With more than 10, it would typically remain and grow and grow.
I guess my main question is, do you think that that's a characteristic of the cluster itself or of its neighborhood of how closely packed everyone is around it to interact with it?
I don't know the answer to that. I could speculate.
Hi, so I actually had 2 questions. My first question is, you mentioned that Gauss had showed that there could be locally a density that was over 0.75, and I was wondering if you ever observed that type of cluster in the experiment?
You can get a local arrangement, yes, with volume fraction up to 75.1% or something. There's no theory for that ultimate limit, but that's an observation in both experiment and simulation, and that's been known in the past too.
And then the second question is, you talked a lot about the role of the boundaries, and I was wondering what you think would happen if instead of the boundary being rigid, it was some kind of more flexible material.
Flexible enough so that the particles could be randomly distributed there.
Yeah.
I don't know what kind of material that would.
I mean, some kind of rubber maybe, or something.
Yeah, but that would exert a force, and I'd just get away from the boundary.
Okay.
Yes, but
Thank you.
Anyone else?
So I saw in the plot for your time scale, or your plot for how the fill fraction increased as a function of amplitude or function of cycles with varying amplitude. That's what I'm
Yes.
trying to say. It looked like there were differing time scales, and the time scale gets faster with bigger amplitude. But it looked to me like maybe there was like a transition where it got very fast right around some larger amplitude. Is there any theory for this time scale?
No. It does, the larger the amplitude, the faster it goes. But there's no theory. Yeah.
No, that seems
It's a new observation. It's just,
okay. That seems like an interesting question to me. And then just one basic question: Did you try to inhibit wall nucleation in the experiment, or was that only in the simulation? In the simulation, you inhibited the wall nucleation. By
in the experiment, definitely.
Definitely,
Yes,
okay.
yeah,
In the experiment
yeah.
as well.
So the particles on the walls of the container were irregularly placed, glued in place, at different heights and different orientations.
Okay, all right. Thanks.
Yeah.
I wasn't sure about that.
There's a question back there.
Yes, so there are transformations in which that don't involve fluids, where you look at the nucleation stages, and in fact, you do see these particles that merge together exactly as you say. They've captured these in atom probe experiments, for example.
Okay.
So the other question I had is that if you look at classical nucleation theory, that the size that you find where you have 10 spheres as your size is usually called a critical nucleus size.
Yes.
And the appearance of a critical nucleus size is inextricably linked to the interfacial energy between the nuclei and the surroundings. And in your case, you don't have any.
There's no Leonard Jones or
Right, exactly.
no
So
interaction.
what takes the place of the interfacial energy in this case that establishes that critical size of 10 particles?
I don't know. Yeah.
This is why I asked you about the pressure.
Yes. Right.
Very interesting stuff.
So, Harry,
There are lots of simulations with Leonard Jones potentials for atoms, and you're
Yeah.
aware.
Yeah.
Well aware.
I'll ask you a question to speculate. If you compare the fraction of papers published in Nature and Physical Review Letters to the total number of papers published that have to do with packing of spheres, must be one of the highest numbers for any discipline. And I wonder, and obviously it's a topic that fascinates lots of people. And I wonder if you were attracted to it, why do you think that is? Obviously, the fact that Kepler was associated with this and Gauss, there is a history. And then at the end, you mentioned Sal Torquato, who dealt with spheres. He got together with Pablo de Benedetti, who was trying to study water. So water is a motivation, but it's probably not the main motivation. So why do you think that so many people are attracted to this for such a long period of time?
Well, I can't answer for other people, but I found it an interesting problem, and it seemed that many experiments and some simulations were doing the same thing or slight variations, and you really wanted to know on the microscopic, on the particle scale, not just the macroscopic scale, what was going on. And we took a while designing experiment, and other people had looked on the microscopic scale in a small way, but they hadn't done this experiment, and so the problem seemed interesting in itself, and it looked like here's a way we can make a contribution. We can look on the microscopic scale in detail, get statistical information, and see how this occurs.
We have a question from our Zoom attendees.
Yeah, there's a question coming in online. Could the fact that small crystallites lose particles to the large ones be analogous to the coarsening seen in the grains of a metal, in which case there's a physical analog to the experimental observation with hard spheres?
Repeat.
One more time? Okay.
Yeah.
Could the fact that small crystallites lose particles to the large crystallites
Yes.
they'll be analogous to coarsening seen in the grains of a metal?
Possibly so. Yeah. I can just say what we saw.
Okay.
But to know to see how crystallites form in water and grow, I mean, there's been an enormous fascination in that problem for well over a century and no understanding.
Any other questions?
So for the numerical simulations, was there a stable percent of particles present in crystallites for the different amplitudes? Was there like a relationship there?
Yeah, for any amplitude in which crystallites grew, then once they were large enough, they continued to grow, and you get, and as the simulation continues, one large crystallite, which is at some arbitrary angle, nearly fills the cell to the size of the container.
Does the percent of the particles that are in that crystallite, is that something that has a relationship to the shear amplitude or any relationship?
I don't know that.
Okay.
Right. But it's only with very large amplitude did we run the simulations large enough to see that you have essentially a single cluster which almost fills the cell out to where there's wall interaction.
All right, thank you.
Did you find any systematic relationship between the crystallographic axes of these clusters you were forming and the axes of the shear deformation you were providing?
No, it's a good question. The answer is no.
To my understanding, the shear force was always like left and right,
Yes.
pushing on the sides. Has there ever been any consideration of whether or not the shear force goes up and down against the direction of gravity?
We didn't in our experiment. Experiments have been done with shear in various ways, with belts, a belt on the top and a belt on the bottom, moving in a loop belt. So you have shear in that way, rather than by moving the walls. Different ways of imposing shear. I don't think it is important how the shear was imposed.
Anyone else? Then let's thank Harry for a wonderful talk.